Today's GEOTOP seminar, we are very happy to have Daniel Peralta-Salas from Madrid, and he will give a talk on approximation theorems for the Schrodinger equation and vortex reconnection in quantum fluids. Daniel, to you.
Okay, good morning, good afternoon, everybody. So first of all, thank you. Thanks a lot to the organizer, especially Renzo, for the kind invitation. It's a pleasure to give a seminar in this already well-established series of online seminars. And as Renzo said, I'm going to talk about vortex reconnections in quantum fluids and related subject, but actually independent of it, approximation theorems for the Schrodinger equation. So let's start. Of course, if you have questions or comments during your talk, I will be happy to answer, so please interrupt me. No problem. It will be great to discuss with you. Okay, Okay. So first, I'm going to introduce the concept of quantum fluid or superfluid from the mathematical viewpoint, which is described by complex valued solutions, so functions that live in R3 times R, because they depend on time, and go to the complex numbers. And they satisfy this evolution equation, Gross-Pitagevsky equation, which is a non-linear Schrodinger equation. This first part here is just the usual linear Schrodinger equation, and this is the non-linear term. And we will consider this is an evolution problem in R3 times R, and we will consider solutions that tend to 1 at infinity, when as the space variable goes to infinity. And this one can be understood as a background quantum potential, a sort of quantum of background potential. But the point of this of the solution U, the modulus of U tending to 1 as x tends to infinity, is so that the Hamiltonian associated to this evolution problem, which is this Ginzburg-Landau Hamiltonian here, it's finite. This Ginzburg-Landau energy is finite. So this will tend to 1 fast enough, this will go to 0 fast enough, and also the gradient of U will go to 0 fast enough, so that this would be finite energy. So we are interested in solutions of this type, and just a comment or a different aspect that this equation takes in the literature, for example, is if you take this transformation, just a time rotation, you define V in terms of U this way, E minus exponential minus ITU, then this converts the Gross-Pitagevsky equation in the following, the focusing nonlinear Schrodinger equation. So it's the same linear part, the Schrodinger equation, and this cubic potential here with a minus sign, which is good because it's the focusing, which means that it has good global existence properties from the PDE viewpoint. And also, actually, this equation appears in other contexts, not only in this context of quantum fluids or superfluids, but also in the context of laser beams. But in this other context, the asymptotic condition that is considered is not that the function tends to 1 at infinity, but it tends to 0 sufficiently fast at infinity. So these are the equations that I'm going to consider in this talk. Then I repeat, that is a complex valued function. So I have to introduce the concept of vortex in this setting. It's different, although related to the concept of vortex in fluid mechanics, which is related to a vector field, the vorticity vector field, integral curves, or something like this. Here, you don't have vector fields in principle, you have functions, complex valued functions. So the definition of quantum vortex at a time t, the fixed time t, is quantum vortices are the connected components of the 0 set of the function u. So you have that u is complex valued, right? So it goes from, if you fix time, it goes from R3 to C, to the complex numbers. So it's 2 functions, actually two real valued functions. So typically these 0 lines, since the function goes to 1 at infinity, they are given by closed curves in space, finitely many, generically. So these closed curves, which could be knotted or linked in a complicated way, or knotted as a trefoil or whatever, these form what we define as the quantum vortices, okay, of the fluid at time t. And this will evolve, this will change with time in general. So in this setting, we can introduce the concept or the notion of vortex reconnection, which is an important feature in the study of vortices in this setting. And it's roughly speaking, or say a definition. It's the following: it's the process through which the two quantum vortices cross, each of them breaking into two parts and exchanging part of itself for part of the other. The typical picture, I will show you a picture in the next slide. So it's the idea is that you have the curve, the two curves, for example, and they evolve with time. After some time, they collide at a single point, typically. And if you continue the evolution, then these two curves become, for example, linked. Or it could be a change of topology of a single curve. So in this regard, we say that this phenomenon, it's of local nature, but has global implications. So this means the following. This means that locally, at the reconnection time, capital T, you have two pieces of different or same vortex lines that collide. As I said, they collide at a point. So that at that instant of time, the quantum vortex fails to be a smooth curve. It's just like an H curve, for example. But globally, this may lead to a change of topology of the curves, modifying the way they are knotted or linked. So a picture here just to represent this reconnection in the context of quantum vortex. Actually, it's a similar concept for in the setting of fluid mechanics, but for vortex lines instead of these lines of these zero lines of the quantum potential. So you have a single vortex. This is a closed curve, which is here in the shape of a trefoil knot, right? And this is a zero line of a solution to the Gross-Mitajewski equation. And after some time, you have that these two pieces, different pieces of the same curve, collide at a point, like a tent, for example, something like this. And there is a change of topology. So actually, you change from a single knotted curve to two linked curves. So in this case, you have a Hopf link here in this reconnection. So this is an example of a reconnection phenomenon in this setting. And actually, in the setting of superfluid helium, there are some experiments, some experimental measures of vortex reconnections. This is a 2D image, and you see here the process I told you. You have here the collision of these two lines. So this is like this figure, right? And then immediately these two curves separate, and you have the separation, and this non-smooth curve becomes the two smooth curves. Okay. And this happens in this context, also happens in the context of fluid mechanics, okay, or MHD. So this is the notion of vortex reconnection. I don't know if you have some questions or comments about just this concept. So I want to emphasize here something that was measured, is that in this experiment, it was observed that the distance between the vortices, vortex means here, remember these curves, or this or the curve here, these two curves, these are the vortices. It was observed a behavior of this type, a T1/2 law, let's say, an exponent 1/2. Capital T is the reconnection time, and the distance between the vortices depend on time in this way. This was a numerical observation, an experimental observation, but actually there are a lot of numerical and also theoretical studies that show that this separation rate is in fact somehow universal, and it's what is known as T1 half law, the separation velocity of the vortices close to the reconnection time, capital T in this case. Okay. There is other phenomenon, this time numerically observed, but also in some experiments, is that the parity of the number of components, of quantum vortices of components, changes at the reconnection time. So look here at this figure. This comes from numerics, from a numerical simulation. This was done by Lou Kaufman, by William Irving and students. And so here you have just a single component, right? This is a trefoil knot, a single component, closed curve. But after the reconnection, this becomes two curves, two closed curves at a half link, right? So this is in fact a sort of universal observation. If you have an even number of vortices, they reconnect into an odd number of quantum vortices, and vice versa. There is always a change of the parity. Okay. So, for example, here is more numerics, very, very interesting paper, a work by William Irvine and Lou Kaufman and his collaborators and their collaborators. So this is numerics for gross Pitagevsky equation. Okay, and this numerics exhibits a cascade of reconnections that transforms this knot, this K62 knot, complicated knot here, at some time equal 1. So there is a cascade. So at the first reconnection process, you have a link. So it's no longer a single knot, but two curves, this and this. Then it reconnects again so that it becomes a single knot, K31. It reconnects again, and then it disconnects, and it becomes another link, this link L2A1. And finally, at the end of the cascade, at the end of all the process, you get the unknot, just a single closed curve, which is the unknot. So we can summarize this saying that this complicated knot, after several cascades of reconnection, always changing the parity so parity here, it's one component, two components, one component, two components, one component, it becomes an unknot, okay, after all this process.
I'm sorry, I have a question. This is Randy.
Yes.
So you're drawing the Seifert surfaces there, right? I think.
Mm-hmm. Yes, so here in this simulation there are in R3, yes.
Yeah. Do the Seifert surfaces change genus each time also? Does the changing of parity also change the genus of the surface?
The genus may change. Yes. I'm not sure it was studied in this work, but in principle, yes, it may change. Yeah, the genus of this surface. Yes. And here they find.
You don't think there's a correlation
between the change of
the change of parity and the change of genus?
The change of parity. I will explain. It's the change of parity. Certainly, it can be explained using, let's say, some Morse theory or some soft topological argument. Yes, I will show you why the parity changes. Yes, generically at least, or in a generic situation. Yes. This is well understood. Yeah, why it changes. And yes, and here the Seifert surface. Of course, there are many Seifert surfaces here. Probably I don't know very well this numerics, so probably Lou or William could tell you better this. Probably here they are considering the natural Seifert surface induced by the function that is defined in the zero set, right? You can define the phase of you have real and imaginary part. You can define the phase. So probably this is what is drawn here, right? But still, in general, this surface may be even non-compact. Okay. So if there are some other questions about this general introduction of the topic, because if not, I'm going to introduce an interesting tool to analyze this phenomenon, which is that we called Pseudo-Seifert surfaces in R4. This I introduce here the pseudo term because usually Seifert surface it's in R3 in the same dimension where the knot is embedded. But here I'm going to consider this in one dimension more, in R4, in space-time. So that's why I call it Pseudo-Seifert. But in some sense, it's the same notion as Seifert surface in R3, but with one dimension more. So let me introduce this definition. So you have two vortex configurations, two sets of closed lines, right, at time 0 and at time capital T. And they are described by two links, this lambda naught and lambda 1. So, of course, I told you that a link is a definite union of closed pairs with joint curves without self-intersections, which are smooth. This is just a link, or a finite union of knots, if you want. So you have the two configurations, right? At time equals 0 and at time equal capital T. So to describe a way of transforming the link, the link at t equals 0 into the link at t equal capital T, we introduce this notion, which is Pseudo-Seifert surface, which is a surface, it's two-dimensional, it's smooth, it's bounded, and it's orientable, surface sigma, in R4, not in R3, in R4, whose boundary is given by, so you have the surface. I'm going to show you the picture already. So you have at t equals 0 this link, which is just a very simple link with two components. Let's say, well, this is a 2 plus 1 picture. Of course, the real picture would be 3 plus 1. So you have a surface whose boundary is at the bottom. It consists of this link lambda naught. Okay, no, gamma naught. What's the name of this? Gamma, lambda. Okay, gamma, maybe gamma, right? Gamma. Keith, what's the name? It's gamma. Yes, gamma naught at time equals 0.
Gamma.
Gamma, perfect. Thank you. And at t equal capital T, you have another link, gamma 1, very simple here, just this unknot, okay? You have this band in this case. And the intersection of the surface with the slice t equals 0, the slice t equals 0, and the slice capital T is just the gamma naught and the gamma 1, okay? This is a condition for this surface. Also, another condition is a genericity condition. We assume it's in generic position, which means that when you consider the time coordinate of R4, time coordinate is just the vertical, right? Vertical coordinate. This is space-time, so this is space. The vertical is time. So we assume that it's a Morse function when restricted on sigma. So this coordinate t on sigma gives you a function, and we assume it to be a Morse function, which is a generic property as far as this is in generic position. A Morse function that doesn't have any critical points on the boundary of the surface. So no critical points here, no critical points here, which means that actually when you consider the time t slices near 0, these time t slices, right, near 0, or near capital T, these time t slices, when they intersect the surface, you will have curves that are isotropic to the original one, close to the 0 and to the capital T time. But when you intersect, but the values corresponding to the time, the values that are critical values of the time function here, this will be the reconnection times actually. So this is what I am summarizing here. The first remark is that this always exists. This even exists in R3, in R4, even more freedom to join two curves with a Seifert surface. It's a very useful way to describe. Yes, sorry. There was a question. I cannot hear. I cannot hear anything.
We cannot hear you.
I cannot. Yeah.
We cannot hear you do it. You have to try to see the settings.
Yes.
And never mind. So,
Oh, now I can hear you.
oh, I see. Now you can hear. So, yeah, this is also
Yes.
known as a Cabordism. So you have this smooth
Cabordism.
Cabordism, and it co-bounds those two links.
Exactly. Yeah, this is Cabordism here that we see embedded in R4. That's right. Perfect. Yeah. Sure. And it's a useful way to describe change of topology using a smooth object. That's the point. Here the surface is smooth, but the reconnection times. But there is a change of topology when you consider the intersection of the time t slice. So you have the time t slices. You intersect with the surface. You get the vortex. You get the closed curve here, and precisely at the critical values, times that are the critical values of the Morse function, you have the change of topology, the reconnection. And actually, this is a universal mechanism to describe a reconnection process for initial and final links in the setting of evolution of zeros of a complex valid function, because you have the time evolution. So you have that the function is defined in space, but it's evolving with time. So you have already this picture of the space and time, and you have that at each time you have the zero set of the function, which is a set of lines, right? But when you move with the time, you get a surface. So actually, this defines a surface in space-time, and generically, this surface is smooth by Sar's theorem, and T is Morse. So this is when you consider finite amount of time, a time region between 0 and capital T, this surface will be smooth. Okay. So this is a sort of universal mechanism to understand reconnections in this setting in this scalar setting. This is very different from the reconnections in MHD setting or in fluid setting, where you have integral curves of a vector field. You have vortex lines, which are integral curves of the vorticity field, and there you cannot describe the reconnection in this way because it's not the integral curves are not the level sets of functions. That's much more complicated. It's a bifurcation phenomena for vector fields, so it's more complicated. And actually, for a generic Morse function, you have that different critical values correspond to different critical points. So different critical points, they will have different values. So using Morse theory in an easy way on surfaces, this explains actually the change of the parity for the number of components of the vortex at each reconnection time. You can see easily an example here. You have here the two curves that collide after some time. You have an 8 curve here now, and then after this time it becomes 1 curve. So this is a universal phenomenon for the change for bifurcation in Morse theory. When you have a generic Morse function, a Morse function with different values for different critical points, you always have this change of parity, right? So this explains in a very easy way why usually is observed this change of parity. Okay, and this is related to Randy's question, but here we are. I think the way of understanding this is using this Seifert surface in R4 in the space-time. In the 3D, the Seifert surface defined by the scalar complex value function, that's more complicated. I don't know, that there might be some connection. And of course, there are also some numerics by William Irvine, by Lou, and by their students that show that there are other sorts of bifurcations or reconnections, which is creation or destruction of quantum vortices. Not only that you have here 2 vortices, 2 lines that collide. Here you get an 8 figure, and here you get a single not. You can have for nothing a vortex appears or disappears, and this of course disappears when you have Morse function with local extrema. If you have a local maximum of the Morse function, right? A local maximum or local minimum, you have that the intersection of the space-time slice may disappear or may appear after some time. This is related to this position of the Pseudo-Seifert surface, of the evolution of the space-time zero of the complex valued function, right? So
and there's no way. Sorry, there's no
yes?
way to get. I'm trying to see. You can't get the standard 3D Seifert surface from the Pseudo-Seifert surface. It's not encoded in it.
It's not. Yeah, it's different. Yeah.
Yeah, I see. Because when you take sections, all you get are the links.
Mm-hmm. Yeah. Mm-hmm. Yeah, exactly. Mm-hmm. Yeah. Mm-hmm. So, and actually, this 3D, yes, that's interesting because there are side connection, but actually, the 3D section is at a fixed time. You have fixed the time, and then you have some complex valued function. You get there the zeros, and you can define the phase locally. You have some Seifert, let's say Seifert surfaces defined by this phase. But the 4D picture, if you want, it's also related to the evolution. So it takes into account how this changes in time. So in principle, it's not a frozen picture. It's actually there is a connection by the PDE. That's for sure, because if you fix things at t equals 0, this will evolve, and this will give you the evolution. But it's difficult, or it's not so easy how to understand how all the topology, let's say, or somehow all the information of the time zero slice will evolve or will give you some topology in the space-time. That's a very complicated non-local problem, of course. Yeah.
I understand.
Very
okay, thank you.
Very interesting. Very interesting. Yeah. So let's state a main theorem in this setting. Okay. So this is just a notation that I'm going to use. So if you have a space-time region in R4 omega, so I will denote by omega t. This is just the time t slice intersected with omega. So omega lives in R4 in the space-time. So omega t is just the time t slice intersection with omega. Okay, and we also use this notation for a dilation. So just simply a dilation with a constant. Sorry, Renzo, what's this? This is what's the name of this Greek? Yes.
What do you mean, eta or
a lambda?
Eta? Lambda.
Yes,
lambda. Lambda subscript eta.
Lambda eta, right? Lambda eta.
We need a Greek course in GEOTOP-A.
Yes. There's no Greek participant today in the seminar. Okay.
Not today.
So you have this. Not today. So you have this. We have this notation. So this is the theorem that we prove with my colleague Alberto Enciso, also from Madrid. So this is the result. So consider two links in R3. Okay. And a Pseudo-Seifert surface, a Seifert surface, a Cabordism, if you want, in R4 that connects this link at t equals 0 with this other link at capital time t. Okay, so you have a time t equals 0, you have a time capital T, you have the two links. Okay. And you connect by any Seifert surface that you want in this generic position that I told you. Anyone that you want. Okay, there are infinitely many choices of connecting the two links. Okay. Then the claim, the result, is that there exists a global solution, uxt, which is smooth, to the Grosby-Tajewski equation in R3 times R, such that it tends to 1 at infinity very, very fast. So this means that this is a smooth in R in time, smooth in time, and in space is a Schwarz function. So Schwarz means that it decays faster than any polynomial. It decays very, very fast. The 1 minus u decays very fast. So actually it's integrable in particular. So this exists for all time, and at each time it decays very fast. Okay? Which realizes there exists this global solution that realizes the vortex reconnection pattern described by this sigma, by this Pseudo-Seifert surface in R4 up to a diffeomorphism. So what does this mean? So this means that for any epsilon and any k, you have this. So there is a constant eta, which is positive. It's small, actually. It's a very small constant. And a diffeomorphism of R4, which is close to the identity, such that when you consider sigma, so sigma is your surface, your Pseudo-Seifert surface, you deform sigma with the diffeomorphism, right? You deform with the very small deformation. Psi is close to the identity, right? And you consider the time t slice of this small deformation. Then up to a rescaling, which is the meaning of this, you have to rescale this process, which actually will mean that you have to compress. It will be very small at the end of the day. The link, so if you have a link of order 1, this intersection just here, this part here is a link of size 1, let's say, in some units. Then this rescaling will mean that you will make it very, very small enough that this is a union of components of the set of the solution, also at very small time, at very small times. There is the eta squared here. Eta is a small constant, actually. And this t belongs to 0 and capital T. So actually, the reconnection process, so you have the two links. They are joined by a Seifert surface, okay? So the theorem says that you can have this evolution of the vortex of the knot with possibly a change of topology, etc. You will have this in a solution to the Grosby-Tajewski equation, but it will be very compressed. It will happen at very small scales of space and time, very small scales of space and time. So the process will happen very, very, very quickly, and at a very, very small scale. That's the point. And you will see why this happens, because this occurs at a linear regime, let's say. We prove the theorem for the linear Schrodinger equation, and then the non-linearity will appear and will be small in some sense, considering this parameter, this small parameter. So this is the idea, that everything takes place at very small region, very small scale of space and time. And in particular, there is a smooth one-parameter family of diffeos, of diffeomorphism, close to the identity, and a finite union of intervals, such that you have, these intervals will be the intervals where the reconnection happens, okay? And then outside the reconnection events, if you want, you have a diffeomorphic evolution. Of course, this is because when you have the Pseudo-Seifert surface, the intersections will be diffeomorphic except near the critical values of the time. So outside these critical regions, everything will be a diffeomorphism. And actually, the separation distance obeys this T1/2 law, and the parity of components changes. So this is the result that we proved. So essentially, summarizing, it says, good point. It says that any change of topology that you can imagine, you have any two links, any links that you want at t equals 0 and at capital T, any two links, and any way of reconnecting it, any way of reconnecting them in space-time, right? Via this Pseudo-Seifert surface, any way that you want. this can be, how to say, embedded somehow into a solution of the Gross-Pytajewski equation. This pattern, this evolution can be embedded there into the Gross-Pytajewski, paying several prices. One of the prices you pay is that this will happen at very small scales of space. So if the picture is of size 1 in space, it will happen at very, very small scales, but also paying the price of very small scale of time. So everything will happen extremely quickly somehow. Okay, so probably not observable from, say, a physical viewpoint. I don't know if there are some questions or comments about the statement before, because now I have a similar statement on laser beams.
Perhaps
So
I
yes?
wonder, Daniel, can you extract any bound on either lower bound, upper bound on this time t.5?
The time where the reconnection happens, well, you fix.
That's right.
Yes. Well, everything will happen very, very quickly. So you can fix this capital T, and all the capital T's. Sorry, all the T's where the reconnection happens can be prescribed, because this is related to the Cipher surface, to the critical values of the time of the Cipher surface. This can be prescribed. But then the problem is that you have this eta square here, right? Which makes everything very small. So there is no quantification of this eta. It's a very, very small constant, which means that everything will happen very quickly at very, very small times. But we don't have a quantification of how small this must be. It's feasible. It could be feasible to using probably a computer-assisted proof and following the proof of the theorem to give a bound for this very small constant. But it could be, I guess, it could be dramatically small, 10 to minus 30 or 10 to minus. I think it could be dramatically small. Yes. Maybe physicists are no longer interested in this. Yes, Keith.
Suppose you have your gamma 0 and gamma 1. Gamma 0 might have, say, 2 components of a link, and gamma 1 might have 4 components. So you would require at least 2 reconnections. Now, when everything you say happens in a very small time interval, does that mean both reconnections have to occur almost simultaneously?
Almost, yeah. Not simultaneously, but it's like a compression of the scale. If one happens, if one happens at 1/2, at the other at 3/4, let's say, then it will be this eta square 1/2 and this eta square 3/4. So actually they are separated, but it's not simultaneous.
Everything. Every reconnection
very fast, yeah.
Everything is happening very rapidly. Okay.
Very rapidly, yeah, very quickly, yes. That's why I said this constant probably is dramatically small. Let's say 10 to minus 30 seconds, or.
Okay.
Yes.
I think
dramatic.
Daniel,
I will show you. Said yes. Sorry.
I think there is an underlying assumption here that I guess you made it at the beginning in discussing the cascade, is that we consider usually one reconnection at a time in order to understand this cascade process, etc., etc. So that's why probably you're in the built-in in your strategy is this assumption of one reconnection at a time.
This is right.
So?
This is right.
Yeah.
This is right.
Yeah.
It's totally related to to this generic position, let's say, of the Pseudo-Cypher surface, that each critical point, in this case the critical point it could appear here, it has a different critical value, different critical points, different critical values. Yes. you could generalize if you want that cascade, that many reconnections happen at the same time. It could be done. I think it's feasible using our technology. And so this could be avoided. What is unavoidable, because at the end of the day, as I'll show you, our proofs are based on linear approximations or linear regimes. What is unavoidable is what Keith said, that this happens dramatically fast. This is unavoidable. Other things can be relaxed, some topology assumption or something like this. Okay. So and now there is an analogous theorem for in the concept of laser beams. I learned actually, I didn't know that this sort of Gross-Pytajewski or nonlinear Schrodinger equation appear in this concept, in this context of optical vortices. I learned this from Mark Dennis, but it seems that they appear, but in this other physical context. But there they are interested not in solutions that tend to 1 at infinity, but that tend to 0. In this case, you have a completely analogous theorem. I'm not going to read it again. It's just you have the two links, and you have the reconnecting the surface that joins them, the space-time surface, right? Then you have the same sort of theorem. Here it's a bit better because you don't have the scale. Here you don't see this eta, this constant, right? That it was needed before. Here everything happens at the scale that you fix. You fix some units. Then you don't need to compress the space and time scale, right? And the reason is the condition at infinity. The fact that here you want that the solution tends to 1 very fast at infinity makes everything more complicated. Since here you want only solutions that tend to 0 at infinity, you can get reconnection times and reconnection patterns of size 1, let's say, if you want. Okay, so that's the difference, the main difference between this optical setting, let's say, and the quantum and the Gross-Pytajewski setting. Okay, same theorem, but without the rescaling, without the compression in space-time. Okay, so let me show you. Here with this I already finished, let's say, introduction and a statement of the results. So now I want to devote the last. So Renzo, how long? Maybe 15 minutes? Do we have 15 minutes?
Yeah, sure.
So now I want to tell you a bit about strategy of the proof. But first, please, if you have some comments or questions about the previous stuff, please ask me.
Interesting what you said about the fact that allowing psi going or u going to 0 is like an inflation in the process, and that's quite interesting. Yeah.
Yes, it makes a difference. Yes, between. So in the Gross-Pytajewski, you want solutions that tend to 1, so that this Ginsburg-Landau energy is bounded. So this, in our proof at least, it's translated into the fact that you have this compression process. For our proof, this doesn't mean that there can be other proofs which are stronger than us. But for the laser beams, since it's the same equation, but you want solutions that tend to 0, not to 1, you don't need this compression in space-time. It just happens at the size that you prescribed a priori. Okay, so let me.
Is it all right if I ask a question, Daniel? Sorry, quickly.
Yes.
If you prescribe a sequence of links, so say 3 links, or what can you say in that scenario? So rather than just the beginning and end, something in the middle as well.
Sorry, so you prescribe 3 links.
You have a gamma 0, gamma 1, and gamma 2, and you'd like a solution that goes from gamma 0 to gamma 2 through gamma 1.
It's a different, at time 0 the gamma 0, at time 1 gamma 1. Yeah, this is possible.
Okay.
Yes. It's just think the idea. It's just you have the links that you want, finitely many, and you put at times. Now, if you are able to find, and you can always to find this space-time surface that intersected at the slices is what you have, then you can realize. Because actually in the proof, what you realize is the space-time surface. This is actually what you realize. So then with intersections, you will get the links. Yes, that's a good question. Yeah. Thank you.
And there's an easy way to see. There's
Yes.
also an easy way to see the change in parity, because you get a change in parity because the curves are oriented, and the reconnection preserves the orientation.
Okay, that's right. That's universal fact, right? That's right. Yeah. Yes. Okay, so let me tell you a bit some ideas about. So this is so the problem is a problem with PDE aspects. Of course, it's a PDE. It's the Gross-Pytayevsky equation. But you have objects that are geometric or topological. If you want, you have links, cipher surfaces. So the rough strategy that we used to approach this problem is okay. So now that I'm going to tell you about the proof, you will see why some assumptions or why some properties of the solutions. This is very important. This first step is that our proofs, because of a reason that I'm telling you in one slide, they are based, or they use very strongly the linear Schrodinger equation, usual I partial TV plus Laplacian V equals 0. So you construct first solutions V to linear Schrodinger equation such that you realize this Pseudo-Seifert surface, okay, as the space-time zero. Okay, so you have the linear Schrodinger equation, and you check that this construction is stable, it's preserved under small perturbations. So now, and this is in a neighborhood. So you construct solutions to the linear Schrodinger equation, but not on all space-time, not on the whole space-time, just in a neighborhood U of the Pseudo-Seifert surface, in a small neighborhood. Okay. Now, you pass from this local solution, from this solution which is defined on this space-time neighborhood, just to a solution which is defined everywhere. You approximate, this is the result, the local solution V by a solution V tilde in all R3 with good behavior at infinity. So now, in this third step, you have a global solution now to the linear Schrodinger equation, which realizes this pattern sigma. But very important to mention here, very important, when you locally in the space-time neighborhood, the zero set is completely prescribed. The zero set is just the sigma. So at each time is the link that you want, but in the space-time region is the whole space-time surface, right? This is the zero set of this complex valid function, and no other zeros. When you approximate the local solution by the global solution, other zeros may appear, and will usually appear actually because it's very isolated in the solution. So actually you will have many other zeros that can be understood as other vortices, right? So what's the meaning or the implication of this? The implication is that in the solutions that we construct, we are fixing our attention to a few vortices, and we are able to understand, let's say for small scales of space and time, but at least you can understand the evolution of these vortices. But there will be many other vortices, many other zeros, finitely many, but many other zeros, that you cannot understand their evolution, okay? And that probably, although they are disconnected from these vortices, but somehow they are interacting with them, okay? That's let's say, this. I didn't think of this till it was a physicist, maybe it was William, or it was someone who, yeah, I think it was William, when I was visiting Chicago. He understood the flexibility, because if you think about this result that we prove, it's quite flexible. I mean, it says you can have anything. You have any two links that you want, any cascade if you want, as Thomas said, and you connect them as you want, and you realize this. Okay, very small scale of space and time, but you realize it. This is somehow, or this is not in the intuition that there could be some obstructions. Okay, a physical idea or point that could help to understand this is that actually these are not the only vortices of the solution. There are many others that may interact with this and may help to have the pattern that you have prescribed. Okay, I don't know if this is clear. Okay, in any case, this is from the mathematical viewpoint, this is behind this approximation, that you have a local solution where you have everything in exact way, but you approximate, and when you approximate, you lose control outside the neighborhood. Okay, and finally, this is for the linear Schrodinger equation. Finally, you promote the linear solution to the non-linear solution, to the solution of the GP equation, using appropriate rescalings or small data solutions. Okay, this is somehow the rough idea of this. Okay, but I don't know if there are some questions or comments about this, let's say, very general strategy. Not very precise, I understand at this moment.
A small question. Are you saying that when you linearize the equation, linear Schrodinger equation, that can admit reconnections in the small time interval, the linear equation?
The linear Schrodinger equation, it's not in the small time. Here you don't need to rescale. Here is just at the time that you prescribe, order one. Yes, here for the linear there is no small compression. Yes, no, you don't shrink anything.
But you can have the change of topology.
You can have the change of topology, defined. Yes. Actually, the same. The same that you have prescribed, this pattern, this sigma, this pseudo-cipher, you have in the linear, right?
Yeah. Okay.
Okay. So let me. Okay. Here now, I want to tell you a bit about an analytic tool that is important to prove that it's this step, the approximation theorem. So what's the idea of this global approximation theorem? So the original motivation is an old theorem by Runge in complex analysis, very classical. Those who gave a course on complex analysis probably had to teach this theorem. So it says essentially the following. If you have a holomorphic function v that is defined on a neighborhood of a compact set K in the complex plane, and you assume that the complement of this set is connected. So, for example, an annulus doesn't work. You have an annulus of the complex plane. The complement has two components, right? The disk and the exterior. So an annulus is not good for this. But in the case that it's connected, Runge theorem says that there is a global homomorphic function, which is actually a polynomial, which approximates this local solution V for any number of derivatives that you want. U minus V in K is smaller than delta. So you have an approximation of the local by the global. And there is a clear PDE interpretation of this, which is a global approximation for local solutions of a PDE. In this case, the PDE is the delta bar operator. Here, the holomorphic functions have solutions to delta bar equals 0. Okay. So actually, this was understood very well and pushed forward and generalized for elliptic PDE with some assumptions by several very strong mathematicians during the 50s and 60s, Lax, Malgrange, Broder, and they prove a very general theorem for elliptic equations, which roughly speaking says that if you have a compact set K with the same assumption, analogous assumption to Runge, the complement must be connected. Okay, and you have an elliptic operator. Then, if your function V satisfies the equation PV equals 0 on a neighborhood of K, it's a sort of local solution, just on a neighborhood of K. You don't have your solution defined everywhere. It's just on a neighborhood of the set. Then you can approximate. Then there is a solution U on the whole space, the whole Rn, which approximates the local solution in the CR norm, any number of derivatives that you want. So it's a global approximation for solutions to elliptic PDEs. So, for example, for Laplacian, for harmonic functions, you have this, or for solutions to the Helmholtz equation, or Yukawa or some other PDEs as far as they are elliptic and linear. This is for linear equations. Okay, then you have this approximation. So the theorem that we prove, which is instrumental to prove the result on the vortices, is this global approximation for the linear Schrodinger equation, and it's an analogous statement to the elliptic theorem. So for the linear Schrodinger equation, you have the same. You have a solution. If you have a solution V that satisfies the linear Schrodinger equation in a bounded space-time domain, omega, okay, and you have some assumptions, okay. Well, V is regular enough. It's L2 HK, so it's HK in space and L2 in time. And you have that the complement, when you intersect this omega t, is the intersection of the space-time domain with the time. Okay? So the complement must be connected, complement in Rn. So this is the analogous statement, analogous assumption to Runge's theorem. Then, if you have a local solution of this time, a solution of the linear Schrodinger equation defining a region of space-time, then for any epsilon, there exists an initial datum, which is Barth, so it decays very fast. Actually, it decays exponentially. It's like a Gaussian, such that the solution to the Schrodinger equation with this initial datum, the W naught, you apply on W naught you apply the operator, the Schrodinger operator, exponential IT delta. Then this solution W, which is global now, approximates your solution in the space-time region as much as you want. For any epsilon, there is this global solution. Okay, so this is the global approximation theorem for the linear Schrodinger equation, which is new and very useful for this setting of the vortices. And here I just want to show you a picture about the topological assumption on the space-time region. So if this set is the space-time region, then the assumption is that when you take the time t slice, each time t slice, this one for example, it gives you these two disks, this and this. Then the complement must be connected, as in this case. Okay, the complement here, the set is these two disks. Is connected. So this is the topological assumption, which is actually a necessary condition for these global approximations. Otherwise, there can be singularities in the interior, in some interior regions. Okay, so armed with this tool, this global approximation theorem, we can prove the results. So now I'm going to skip a bit some of the steps. Probably, well, here there is an interesting step, which is about this T1/2 law, which is very much related to Moore's lemma. Why T1/2 law is satisfied in our case? Because the reconnection happens at the critical values of the time function restricted to the surface, right? But near the critical points, you have that the function is of this type. It's a Morse function. This is Moore's lemma. So this actually implies near time, for times near the reconnection time. This implies that the distance grows like T1/2 because of this quadratic Morse part, and then the value of the function of the time. Okay, a very soft argument using Moore's lemma. So now, just to finish these ideas of the proof, I want to show you how this rescaling, this mysterious rescaling factor appears. It's simply because we do everything, as I said, with the linear Schrodinger equation. So just this part, the linear Schrodinger equation. So actually what we consider is a small perturbation of the linear Schrodinger equation. So we put a delta here, okay, a constant delta, in front of the non-linear part, okay. If this delta is small enough, using Duhamel's formula, you can check that the solution to the linear Schrodinger equation and the solution to the non-linear with the same initial datum same initial datum solution to linear and the full nonlinear, they are very close to each other for finite time, not globally, of course. For finite time, you fix the time, they are very close if delta is small enough. Okay, so then you have a solution to the nonlinear GP equation, but with a weak nonlinearity, weak in the sense that you have a delta very small constant here. Okay. Now what you do is you rescale. If you rescale the space and the time this way, you will get a solution that satisfies the GP equation in the original scale, but now you have rescaled the process, the time and the space region of the process, so everything will happen very quickly in time and very small in space. Okay, that's why this scale appears in the statement of the theorem. For the optical vortices, you don't have this because well, you have the equation, the GP equation. You can write in this other way. This is equivalent to the other way of writing this. But now, since you want that solutions tend to zero at infinity, the trick that you can use now is not rescaling in space of time, but just simply considering solutions that are small. So the complex function, the complex valued function, it's a delta 1/2 times a solution that is close to the linear Schrodinger equation. So now there is no scale of the scaling of the space-time region, but it's small solutions, okay? Small functions. So I'm almost done. So just to summarize, I want to tell you a few remarks. It's the first one. I already emphasized this. It is that these prescribed vortices occur at very small scales of space and time. And actually, if you followed the proof and did some precise estimates, probably not by hand, but using a computer-assisted proof or something, this constant is actually very, very, very small. It will be very, very small. Second, as I already mentioned when I explained the statement of the theorem, there are other vortices. We are not prescribing all the vortices that appear in the picture, that appear in the solution. So we are prescribing in an efficient way how these vortices behave and how they reconnect. Small space and time scale, but we prescribe in a precise way. But we don't know what happens with other vortices that necessarily will appear because of the global approximation. Because you have a local solution, you approximate by global, the global will oscillate quite a lot and will create many other zeros. Finally many, but many other zeros. And a final remark, if you're interested in rotation or winding number, sometimes people studying this stuff are interested in the angle. Let's say if you consider the phase, so you have locally you have the real and imaginary part of the functions. This is what Randy said how to define, at least locally, the Cipher surface. You can define a phase, etc. Okay, people are interested in if in this phase makes 2 pi, or how many turns it gives, because it could be degenerate or so. So here it's everything. It's non-degenerate. So the winding number is 1 for all the vortices that you prescribe. So it's actually the real and imaginary part are like local coordinates of a neighborhood, of a trivial neighborhood of the node or of the link. Okay, so it's winding number equal to 1. Okay, so I hope you enjoyed a bit the talk, and that's all. Thank you for your attention.
Thank you very much, Daniel. A very interesting talk. So I just welcome questions from the audience.
Yes, I've got one thing to say. If you've got 2 oriented links in general, it's not always true that there's a Pseudo-Seifert surface connecting them. Sometimes it is, and sometimes it isn't. So this is the so-called link Cabordism problem. And
because of the orientation.
Yeah, because of the orientation. So there's a link Cabordism group, and it's a very large abelian group, infinitely generated. So Pseudo-Seifert surface exists between these 2 oriented links if and only if they're the same element of this link Cabordism group.
No, but I'm not orienting the links. So it's just two curves in space and time.
Clever. Okay.
So I'm not oriented. So without orientation, it always exists, right? So yes, I don't orient the link. Yeah.
Okay.
Then yes, definitely yes. If you orient, there will be abstractions, right? That's true. Yeah.
Okay.
Mm.
Any other questions?
Just like say, brilliant talk. Thank you, Daniel. Lovely.
Thank you.
Wonderful.
Thank you, Keith.
Thank you, Daniel. Thank you very much.
Well done.
Thank you, Ron. Actually, this name of pseudo, I don't know. Lou is around. Not today. Lou Kaufman.
Not today, it seems.
No, it's not. Not today. He suggested the name of pseudo. I was in Chicago. I usually visit William Irwin. So I also visited Lou in he's at UIC, right? And talking about this, he suggested the name pseudo because first I used just Cipher surface, but he said that Seifert is usually or it's used mainly for the three-dimensional stuff. So yes, then we changed to Pseudo-Seifert. Still, I don't know if it's a good name. Maybe it's better this Cabordism that the Witt said, but we are not orienting the links, so it may be misleading.
Yeah, usually it's oriented in the Cabordism world. So
right, in the Cabordism it's oriented. So here, that's Pseudo-Seifert.
Yeah.
But Danielle, would you have an orientation given by the rotation of the velocity in the Gauss?
You could, yes, you can orient. Then yes, okay, you could do the construction orienting. Then you need to take into account these abstractions that the Witt mentioned just for the existence of the Pseudo-Seifert. And then one also has to be careful with the local construction of the solution. But in principle, yes, you can orient you can give an orientation, yes, because you have the local, the real and imaginary part, which will give you the orientation. Yes, definitely, it could be prescribed. Yes, and also you could prescribe the trivialization of the normal bundle of the link given by the fibers of the. This can be chosen, I think. So you have the real and imaginary part, right, of your complex function, and it gives you fibers because it's the level lines. So I think you can also prescribe. I don't know if a total will, but you can play with different trivializations of the bundle, of the normal bundle. Yeah. But we didn't.
Great talk, Daniel. Thanks a lot. Yeah.
Thank you. Who's speaking?
Do you
Who's
have
speaking?
Gunnar? Can't you see me?
Oh, hello, Gunnar. How are you?
I wonder if, from your theory, do you have any chance to estimate the symmetry, time symmetry or asymmetry across the reconnection? Is any information about that? Just the before and the after.
What do you mean by time symmetry, or?
Just the before and the after. If this power law is holds true for just the time just before the reconnection, the moment of reconnection, and also after the reconnection. Because in some cases it seems that there is a time asymmetry across the reconnection, and I was wondering if you have any information about that.
Yes, well, with respect to what happens with the link, let's say, if you want, everything is prescribed in the Pseudo-Seifert surface that you give. So you give in a space-time the Pseudo-Seifert surface that joins the two links, and at the critical values of the time the reconnection happens. So the way that the link changes is somehow it's you can read it from the surface, because we are somehow embedding the surface into the evolution of the
Sure,
equation.
it's
So any sort of asymmetry or
yeah.
Yes, sorry, Renzo. That's
No,
concerning this part of the evolution.
That's
because
okay.
there are many other.
Sure, I would interpret that as a sort of kinematic picture rather than dynamics, because you know, if there is any difference between the before and the after, then as you said, is just somehow encapsulated in the picture you give. So it depends on the picture somehow. All right.
That's right. Yeah, yes, that's right. But yes, a point that I'd like to emphasize is that, and you, Renzo, and Keith, and everybody who has worked on the fluid vortex reconnection, is that this strategy, this way of understanding, it's maybe it's better way of understanding reconnections in scalar problems. It's completely useless for. I think completely useless for fluid reconnections, because this is very well adapted to a problem that consists of level sets or of zero sets of complex values function that change in time. But for vector fields, the vorticity field or the magnetic field for the MHD or whatever, you don't have these level sets. I mean, this map. So that's why there it's so hard to understand all the phenomena. Also, other reason is, of course, that Navier-Stokes is more complicated than Gross-Pitayevsky, but
yeah, I agree. This is beautiful, because we deal in effect with defects, with nodal lines, and so everything is crystal clear, so to speak, at least in terms of geometry.
Exactly. Yeah, otherwise you have integral curves of a vector field, orbits of a vector field, and that's difficult to to analyze.
Okay, if no other questions, well, we all thank you again, Daniel. Wonderful talk.